Welcome back, ladies and gentlemen, to another video with Mr. Kenton. We are rolling along in Unit 1. We actually have 2 more topics to cover in this unit, and so we're getting close to the end. And so, but this next topic, really good, really important, periodic trends. I think it's going to be a review, but there are going to be some new pieces that we're going to add to this. And I do just want to add that if you're keeping up with me here, now that we've finally finished up Chapter 6, we can kind of transition into Chapter 7. So you've got some new bookwork problems that you can do. I know that makes you excited. That means you can do more problems so that you can better prepare as we go forward. So without further ado, let me introduce some of the background information for periodic trends before we talk about the actual periodic trends, okay? So first, there's this idea, when we think about the word periodic, it's important to understand that it doesn't just simply mean that it happens every now and then. In fact, the word periodic, when you look at periodic table, periodic actually refers to these specific patterns that follow. And so the periodic table has what's called a periodic law. When we arrange the elements in order of increasing atomic number, there is a predictable pattern in the physical and chemical properties of the elements on the periodic table. And so we're going to dive into what are those periodic patterns? What are these things that we can predict as a result of the elements being arranged based on increasing atomic number? Now, this is going to tie directly back to electron configuration. So if you've noticed, we've been building every single step of the way. We've been building on our knowledge leading up to this particular point, right? Now, what we know when we look at the periodic table is that the elements that are in the same column or the same group have similar valence electron configurations. And what I mean by that is that their final electron configuration is going to end the same. So if we're talking about the alkali metals, for example, they're all going to end in S1. The last electron is going to be S1. If we're talking about the halogens, it's always going to be S2P5. The P5 is always going to be that last component of its electron configuration. And that's going to be indicative of the column that the element belongs to. The fact that the electron configurations, specifically at the valence level, are similar is actually going to explain why the chemical properties of elements that are in the same column are similar. That's why we call them families, right? Because they have the same number of valence electrons. Now, we can look at something like the alkali metals, for example. They all readily lose one electron in their s orbital, so they can have that noble gas configuration. We know that our noble gases, when we look at their electron configurations, all of their valence electrons, their valence orbitals have been filled. And so because their valence electron orbitals have been filled, the noble gases are unreactive. The transition metals are filling in the d orbitals, and so as a result, when you start to look at the different ions that they form and the different colors that these metals burn when they're placed in solution, we get colorful and multivalent ions. We got like copper 2+ and copper 1+, iron 2+ and iron 3+, right? And so looking at an element's electron configuration actually helps us understand some of those periodic trends as well. Now, as we've kind of broken that down, I need to take some time to talk more about effective nuclear charge. Now, you should remember this from the Coulomb's law video that you watched a couple of videos back. And so if you're remembering, effective nuclear charge has to do with the attraction between the protons in the nucleus and the electrons. Now, we're going to kind of define it right now as the actual positive charge specifically felt by a valence electron. Okay. Now, to calculate effective nuclear charge, or ZEFF, what we're going to do is we're going to take Z, which is the atomic number, and we're going to subtract the number of core electrons from that. Now, this is going to be an approximation. This is not actually how effective nuclear charge is calculated. This is an oversimplification, and I think I mentioned that previously in the video before. Now, when we look at each of these elements, we've got their atomic numbers Z. Sodium's 11, magnesium's 12, aluminum's 13, silicon is 14. Now notice all of these elements are in the same period or on the same row of the periodic table. So the only thing that's going to change is going to be their Z and their Z effective. So the number of core electrons is the same for each of them. They each have 10 core electrons. Like if you were to write the electron configurations for each of those things, you would see that they have 10 electrons that are occupying the first and second energy levels. Now, plugging that into our equation, what we're going to find is that sodium has a +1 effective nuclear charge, magnesium's +2, aluminum +3, and silicon +4. And so that means that when we're comparing these two, the actual positive charge felt by a valence electron within silicon is going to be stronger than the effective nuclear charge that's felt by the electron within sodium. And that has to do with the fact that there is more protons in the nucleus of silicon as compared to sodium. Now, the trend in effective nuclear charge. It is going to increase as you move from left to right across a period. We saw that from the data on the previous slide as we went across from sodium to magnesium to aluminum to silicon. We saw that the effective nuclear charge went up. Now, this particular trend is really only going to be meaningful as we move left to right. It's going to essentially stay the same as you move down a group on the periodic table. Now, again, we've already looked at this, right? But how we got to this, the electron configurations that are in green, those correspond to our core electrons, and then our blue electron in our 3s orbital is going to be our valence electron. So it has one valence electron, it's got 11 protons, 10 core electrons, Z effective is going to be +1. And this is looking somewhat at a Bohr model. We know that's not the best model, but that's just a quick and easy way for us to take a look at that. If you look at magnesium, again, the core electrons stay the same. These two electrons here, those are going to be, the Z effective for each outermost electron is going to be +2. So each electron that's in the valence shell for magnesium experiences an effective nuclear charge of +2. If we look at phosphorus, for example, okay, phosphorus has 10 core electrons just like everything else we've looked at, but then you've got that 3s2, 3p3, so those 5 electrons each experience an effective nuclear charge of +5. Now, effective nuclear charge, I think you probably have a good grasp of how that works. You're just looking at the atomic number, the total number of electrons that it has, subtracting the core electrons from it to come up with this value. Now, the other thing that we have to consider when this is happening is going to be what's called shielding. So those valence electrons, when they're trying to interact with the nucleus, they're going to be repelling each other. And the core electrons are also going to be repelling them. And so that's what leads us into this idea of shielding. Now, this is this is going to be described as a screening effect of the core electrons, right? Because what happens when two negatively charged particles come in contact with each other? If you remember from Coulomb's law, we get a positive electric force, which means they're going to repel. They're going to try to move away from each other. So those core electrons are going to prevent the valence electrons from feeling the effects or the pull of the nucleus on those valence electrons. Now, shielding is going to reduce the effective pull of the protons in the nucleus for a given valence electron. Now, the core electron shield view of an equivalent number of protons in the nucleus. Therefore, if we break that down, that statement, that means that any one valence electron is going to see lower numbers of protons at the nucleus, okay? Because essentially those core electrons are going to prevent that particular pull, because there's going to be the repulsions of the electrons trying to balance out the pull of the protons. Hope that makes sense. You got this idea of shielding, where the protons are being shielded by the core electrons. So that prevents the valence electrons from interacting with the nucleus. Now, when you start to talk about shielding, right, it's going to stay the same as you move from left to right across the periodic table. Well, that should make sense, because the number of core electrons is not changing as you move across a period. So shielding is not going to really change all that much as you go from left to right. But as you move down a group, shielding is going to change, because you're going to add a completely new set of core electrons, which are going to increase that shielding effect from those core electrons. I hope that makes sense. Now, as we're going from left to right in a row on the periodic table, what we should see, effective nuclear charge, it increases. Shielding remains the same. As we go from left to right, the number of protons in the nucleus increases. The core electrons remain the same as we move left to right. And so as a result, we have to think about, what about the screening of those valence electrons? Well, the reality is those additional valence electrons don't really screen each other all that well, so it's rather ineffective. Let me go back there for a second. So this is just a good summary of what we've talked about as it pertains to moving left to right on the periodic table and summarizing what's going on. Now, the next slide is going to summarize what happens as we go down a group. So what we've seen is the distance of the valence electrons from the nucleus increases. So as a result, the attraction between the valence electrons and the protons in the nucleus decreases. That should remind us of Coulomb's law. That makes a lot of sense. The distance is increased, so the attraction has also decreased. And so because of this, there will be less of an attraction for electrons from other atoms, and electrons that are there aren't as tightly held on to. And if we're thinking about how that corresponds to our shielding, the shielding effect is much stronger, which is why it's easier to pull off or to lose a valence electron on a larger atom. Now, a word before we start diving into the periodic trends. AP really wants you to focus in on effective nuclear charge and Coulomb's law as explanations for periodic trends. It's simply not enough to talk about you've memorized the trend, right? I know for honors chem you could probably get by with that, but for AP, it's going to be extremely important that you tie the periodic trends that we look at back to effective nuclear charge and to Coulomb's law. Now, when we start to look at this and break this down, effective nuclear charge is going to increase across the period. We've seen that. So that means that the attraction or pull from the nucleus is going to increase. So it's going to have a stronger attractive force as we move across the period. Okay, the second piece here, due to Coulomb's law, as distance from the nucleus increases moving down a group, we get decreased attractions down a group due to that increased distance from the nucleus. Both of those ideas are going to help us better understand size, ionization energy, electronegativity, electron affinity, metallic versus non-metallic character. All these different things, we should be able to explain the trends using both of those pieces of information, effective nuclear charge and Coulomb's law. Now, here's the last thing I want to do. I just want to briefly introduce all of the periodic trends, and then I'm going to take time to make videos to analyze several of them in pairs and some smaller videos here. So here are the periodic trends that we need to be familiar with. So these periodic trends, they can be predicted using the periodic trends. We've got atomic radius. We've got ionic radius, which leads us into cations and anions, which we'll define later. You've got ionization energy, electronegativity. All of those things, I hope, are not new to you. But then we've got electron affinity. That's new. Then we're going to look at metallic character and reactivity, non-metallic character and reactivity, and then oxidation states. Now, ladies and gentlemen, there's a lot here in this kind of intro video to periodic trends. But again, the big thing is looking at effective nuclear charge and shielding and Coulomb's law. How does that help us better understand these particular trends? Okay. Thank you so much for joining me. I hope this video was helpful, insightful. Obviously, if you come to class, if you watch this and you didn't understand something, feel free to ask me a question. I'm more than willing to walk through that and help you with it. Thank you guys so much. Hope you guys have a great day, and I look forward to seeing you guys again soon.